The goal of this video is to derive the formula for the tangent slope of a polar curve. So here's the big question. You have a polar curve and you pick a point on the curve and you'd like to know, as a function of theta, the input variable for the polar curve, what is the value of the tangent slope dy dx? So what makes this problem hard is when a formula is given to you as a polar formula, you have no immediate access to x and y. We're going to have to work a little bit to find dy dx in terms of theta. So what we'll do is we'll zero in on the point where we want to find the slope, and we'll assume that near that point the curve is not vertical. And we'll use that fact in a second. So how are we going to go about finding dy dx? In a nutshell, the chain rule will come to the rescue. So how's that works? We're going to make a few observations. The first is that at least for the part of the graph we've chosen, y is a function of x. Why? Because we chose a point where the tangent slope's not vertical, so nearby the graph passes the vertical line test. So y is a function of x, even if it's implicit. X is a function of theta. How do we know this? We know x is r cosine theta. R is a function of theta, so we could plug that function in and we would have some function of theta explicitly. Similarly, y is also a function of theta. Now what do we have? This is a composition. We can get from theta to y immediately, or we can go through the intermediate variable x. So this is a composition, and we can apply the chain rule. The chain rule says that dy d theta is the product of dy dx and dx d theta. If you solve for dy dx, you get the quotient of these two derivatives, dy d theta over dx d theta. This doesn't look perhaps a whole lot better, but actually dy d theta can be obtained via the product rule from y equals r sine theta. And similarly, dx d theta can be obtained via the product rule. And when you plug those in, you get a formula for dy dx, and you'll notice that everything on the right-hand side of the equation is a function of theta. You have r, which is a function of theta, dr d theta, once you take that derivative, that will be a function of theta, and of course cosine theta and sine theta are functions of theta. So all that information gets dumped into the formula, and there's your formula for dy dx. And that's the answer to our question. So let's look at an example. We're going to start with an example where we already know the answer through basic geometry, so we can have something to check against. Find a formula for dy dx as a function of theta for the polar curve r equals 1. The polar curve r equals 1 is particularly simple. It's the unit circle. So the first thing to notice is when you look to apply this formula, dr d theta is 0. R is constant. And that means about half of that formula just drops right out of the picture. And the r's, which are both 1, but they cancel. You can either substitute 1 or they cancel, either way you look at it. And now dy dx is negative 1 over tangent theta. So let's see why this is correct. You have over on the left side your picture, and you'll notice that whenever you're on the unit circle, the coordinates are cosine theta, sine theta. So the slope of the line containing that orange radius is sine over cosine. That's tangent. The slope of that line is tangent theta, and we're looking for a tangent line to the circle, and we know from basic geometry that's going to be orthogonal to that line. And so how do you find the slope of such a thing? You'd take the negative reciprocal. That'd be negative 1 over tan theta. So our formula works. And if we go to write down the formula, we might call that cotangent instead. So dy dx is negative cotangent theta. That tells you the tangent slope as a function of theta. Example B, find a polar equation for the line x plus y equals 2, then find a formula for dy dx as a function of theta. So once again, this is a case where we know the answer already. It's very obvious that the slope is negative 1 everywhere on this line. So the point is not to somehow use this more complicated method for finding the slope. We know what the slope is, but we want to choose an example where it makes it obvious that this thing's working correctly. So x plus y equals 2. We can replace x and y with the conversion formulas r cosine theta, r sine theta. Factor the r, divide out by cosine theta plus sine theta. There's our polar equation, our polar curve, r explicitly in terms of theta. Dr d theta, we can apply the power rule, the chain rule, simplify that a bit, and there's our derivative. So now we're going to plug all of this information into our formula for dy dx. We have to substitute r, and we have to substitute dr d theta. And wow, okay, now we should not panic, and we should definitely not just start expanding things willy-nilly. Take a moment to look at this. There's some strategy here we could use to make life better. You could clear out the fractions top and bottom by multiplying 1/2 quantity cosine plus sine squared. And a lot of that is going to simplify. Now the expression you have is much easier to deal with, and if you expand that, in fact, you get some nice cancellation. And cosine squared plus sine squared on the top is 1, negative sine squared minus cosine squared on the bottom is negative 1. Lo and behold, our formula actually gave us the right answer. In fact, it simplified all the way down to negative 1. Independent of the value of theta, dy dx is always negative 1. So let's use our formula to find the tangent line to a graph, and we want the Cartesian equation. So we've got r equals 3 cosine 3 theta, and we want to choose a point where theta equals pi over 4. So the first job is to figure out where that point is. Theta equals pi over 4 gives us the direction that goes off in the first quadrant, like so. And when we plug that theta in to find r, we find that the radius is actually negative. So we have to march backwards 3 root 2 over 2 units. And we can apply r cosine theta and r sine theta to find the values of x and y. And so when all the dust settles, the point we're looking for has Cartesian coordinates negative 3/2, comma negative 3/2. Next, finding the tangent slope. Here's where we use our new formula. Find the derivative dr d theta first. That's negative 9 sine 3 theta. And when theta equals pi over 4, dr d theta is negative 9 root 2 over 2. So now we're going to plug in the value of r and dr d theta and cosine theta and sine theta. Once again, use some strategy here. You can multiply through top and bottom by 4 before you start simplifying, and you get dy dx equals 2. Point slope formula, the equation of the tangent line is y plus 3/2 equals 2 quantity x plus 3/2.